For many years, architects and historians have marveled at the durability and longevity of Roman concrete structures like the Pantheon, which remains the largest unreinforced concrete dome even centuries after it was erected. These buildings seem even more impressive when compared with modern concrete constructions like roads, sidewalks, and foundations that have to be replaced at least every 100 years. The secret of how the Romans were able to build such durable cement buildings lies in the chemistry of the mixture. Both modern and Roman concrete are made by mixing water, limestone, and some other minerals to create a malleable and durable building material. In both cases, the primary reaction taking place involves calcium, carbon dioxide, water, and silicon dioxide, and can be broken up into 3 steps. In the first step, calcium carbonate is heated to over 1,000 Kelvin to induce its decomposition into calcium oxide and carbon dioxide. This forward reaction is endothermic, meaning it consumes heat energy, and results in an increase in entropy. When we consider the Gibbs free energy equation, which states that the change in Gibbs free energy is equal to the change in enthalpy minus temperature times change in entropy, it makes sense that calcium carbonate needs to be heated to a high temperature to decompose. Delta G will only be negative at high temperatures because both delta H and delta S are positive. We can find the exact temperature at which the reaction becomes spontaneous by using the experimentally measured values for delta H and delta S of calcium carbonate. For the forward reaction to be spontaneous, we need delta G to be negative. We can solve for when the reaction becomes spontaneous by setting delta G equal to 0 and solving for the temperature value. Doing this, we find that T equals delta H divided by delta S. Plugging in the values for delta H and delta S, we find that the reaction becomes spontaneous around 1108 Kelvin. When this reaction takes place, carbon dioxide and calcium oxide are formed. Water is then added to calcium oxide, also known as quicklime, to create calcium hydroxide or slaked lime. This slaked lime is then added to sand or rubble to thicken the mixture. Modern concrete is typically mixed with sand, and Roman concrete was mixed with a type of volcanic ash called pozzolana, after a town named Pozzoli, where much of this ash was sourced from. Both sand and pozzolana are primarily comprised of silicon dioxide, which reacts with slaked lime and more water to finally form concrete. So far, modern concrete and Roman concrete are nearly identical. However, Roman concrete has been able to withstand fires, natural disasters, and foot traffic for centuries, while modern-day concrete needs to be replaced regularly. It turns out that what sets Roman concrete apart is the incorporation of unreacted quicklime in the mixture. For many years, scientists assumed that the presence of quicklime was a product of poor mixing skills or impurities in Roman concrete, but research from MIT professor Admir Masick suggests that the lime gives the concrete self-healing properties. Masick's findings indicated that Romans used a process called hot mixing to incorporate quicklime into their concrete. Because quicklime spontaneously reacts with any moisture to form slaked lime and releases a lot of heat in the reaction, the Romans used a process called hot mixing to shift this reaction back towards quicklime. Heating the solution of slaked lime, water, and pozzolana results in pockets of quicklime called lime clasts to form inside of the hardened concrete. When the concrete undergoes stress, cracks form and travel towards these clasts. As moisture from the air or from precipitation seeps into these cracks, more slaked lime is formed, and the unreacted quicklime begins reacting to form more concrete in these cracks. Over time, as more cracks form, new concrete fills in the cracks, strengthening the structures. Many modern-day construction and concrete experts are advocating for the use of similar strategies in concrete mixing today. Seeing as concrete is the second highest consumed product, second only to water, creating a modern-day self-repairing concrete would greatly impact global emissions and resource use. In fact, the emission of CO2 in the decomposition of calcium carbonate is the main reason that concrete is responsible for 8% of global carbon emissions. Although the Romans didn't have all of the technology that we have today, their expertise in building materials could prove to be very useful in tackling modern problems like resource consumption and carbon emissions. Researchers today are continuing to look into these ancient practices to see how we can utilize them to build a more sustainable tomorrow.